As Harriet said, I'm at Scion. I kind of got turned into the last man standing in a lot of ways for the turn of species work. But a lot of this work that I've been there for almost 7 years now, and a lot of this work has been brought on the shoulders of giants that come in the past, like late Neil Barr and late Ian Nicholas and late Alan Levitt. So just keeping the knowledge going and making sure it's not lost and building it up and see where we go. Oh, I'm going to push the... Oh. How about I just do the old-fashioned way? You know. There we go. Yeah, just that thing. So my presentation is kind of this outline of first talking about ecosystem black box and drivers of productivity, before discussing process-based modelling and the importance of return of species, before bringing out how my project revolves around this project from the MPI, predicting productivity of carbon sequestration as potential for Eucalyptus species, for sum it all up. So there's multiple site factors that influence productivity that Ewan had touched on earlier. So temperature is quite important, obviously. Rainfall, not only just monthly rainfall, but rainfall over different periods of the year. You know, like in the summer periods, how long that dry period is can influence productivity. Frost days, solar radiation, as well as water storage capacity of the soil over winter months to supply water to the trees over the summer months. And potential rooting depth. So there's multiple site factors that influence productivity. The traditional approach in forestry is the black box approach, not understanding how these various processes interact. So traditional forestry methods was you go and plant your tree species of choice, try a whole bunch of tree species and management techniques, go away, come back 10, 20, 30 years later, and decide which ones has worked the best. So it works. It's built from the forestry sector for the last couple of hundred years throughout the world, but it takes a bloody long time and involves a lot of plots, and it can be rather expensive. And to me, as a scientist, what bothers me the most is you don't even have a clue what's happened in that black box. On top of that, we got climate change issues coming through. We're talking about, with the older projections at the moment, we're around a 1.6 to 2 degrees C average temperature rise by 2018, as well as rainfall changes from plus or minus 10 to 15%, which doesn't sound like a lot, but it can, especially in the Northland and the east coast of both islands, that can have a huge effect, especially on how long those dry periods occur over the months. And traditional empirical-based modelling doesn't have the ability to kind of investigate what those impacts of climate change would have on those different species and how productivity will work in the future. I always like to think of stand productivity, the ecosystem black box, as this kind of figure. So you've got a range of different things going on affecting trees' growth. So you've got from genetic stuff like photosynthesis, transpiration, carbon allocation, to site conditions, a whole bunch of soil, rainfall, climate conditions, soil fertility, topography, as well as weed competition, as well as competition between trees themselves. And most importantly is that they all individually influence sound productivity in different ways. But they also interact with each other. So there's a complexity of interactions going there, both directly on the tree growth and indirectly on the tree growth. Now, empirical-based modelling for radiated pine has been based rather successfully from back in the heyday of about 10,000 individual research plots from the individual plantations throughout New Zealand. I think they currently act around about 5,000 data plots, and it has produced like 300, like a site index for productivity throughout New Zealand. However, the issues is that you need thousands of plots over a very long time period to develop such good empirical relationships. It is the ecosystem black box approach. Empirical model is static, not dynamic. You can't bring in what-ifs to new environmental site or management or conditions that could be affecting your forests. And the last one is radiopine is not as site sensitive as other species. So just because radiopine grows here doesn't mean your species of choice will grow there as well. So it doesn't make a good proxy for other species. The alternative modelling approach is using process-based modelling. You touched on this earlier, where you kind of bring in some ecophysiological responses to growth of a particular tree species, of bringing up why a tree species grows as it does, how environment affects productivity in terms of photosynthesis, respiration, water usage, etc., etc. So if you understand the whys of a species, or how it grows and where the major limitations are, and what its site sensitivities are, then you can use the model to project how the growth of a species on a new site that the tree species has never been grown before, and give a good range of what it's going to perform. I won't give you, actually the 100% precise number, but at least you can say it's going to be a good site or a bad site, if it's to be a good place to grow or not a good place to grow. That kind of method is really good for dealing with alternative species from non-radiated species from all the dryland Eucalypt species approach, where you don't have much data, and you need to trying to quantify the growth and trying to say where's a good place to grow and where it doesn't grow very well. So my project that's is through MPI is under the Sustainable Land Management and Climate Change program called SLEMAX. And it was to quantify the productivity and carbon sequestration potential of Eucalyptus globoidea and Eucalyptus regnans. As you all know, the carbon market is a wee bit defunct at the moment with the current prices. But hey, there was some money to do some research with the Eucalypt, so we had a sneaky way to get some more data for developing new models, new process-based models for these species. The project also gave us a chance to collaborate with the dryland forestry group, is to collect some data from existing globoidea stands that have been established by FRI and farm foresters or corporate forests, to get some data of globoidea stands and see how they're grown throughout the country at various ages, like I think the youngest around age 8, age 9, right up to age 30 or 40 years old. So we can have some hard numbers of how these species grow. And of course, this work is not starting from scratch. It is building from what has been done before. So Eucalyptus fastigata is one of the euc species that we actually have a lot of data for. A lot, as in there's probably about 50 odd data points, 60 odd data points throughout the country with a good geographic spread. And that has been used previously for my work on process-based modelling or predicting fastigata productivity and carbon sequestration. So this was used, this is where I used Eucalypt 3PG to produce a Eucalyptus fastigata productivity map to give a general nationwide prediction of productivity throughout New Zealand. And this can be, if you zoom into this one area, so you look at this nationwide map, so you kind of a bit of a so what. If you zoom into this area around the BOP, you start getting more and more details of stand productivity, which is stand volume per hectare at age 30 for this stocking regime as its plant and leaf, as an old carbon regime. And if you zoom further and further into the map, you get more and more data until you get down to a grid size of about 500 metres by 500 metres. And those numbers are individual predictions of productivity through this particular stand, a particular location in New Zealand. Now, I did promise Paul a map for globoidea, but I haven't quite got there yet. But this is where this mapping is going, and it is to give this spatial ability of not too much giving you the hard number what the number is going to grow at a particular place, but it will give you an idea on a nationwide map on regional area where areas where globoidea will be more suitable than other areas where it will be less suitable. The work that Ewan is busy doing will give a lot of detail on at a finer scale in terms of microsite variations and aspects and etc. So this is the Eucalypt maps of various research plots, data points we have for fastigata, globoidea and regnans. As you can see, the distribution is kind of a wee bit scattered all over the country with With globoidea, a lot of it focused on near or on coastal areas around most of the North Island. Regnans, there's a whole bunch of regnans planted around the central North Island and scattered around different parts, as when Fascicata is scattered around then. So part of this MPI project is to say, well, can we lean on the work that we have done previously with Fascicata in terms of nationwide productivity, nationwide identifications of limitations of growth, if there's similarities with Fascicata, to kind of lean on that to establish relationships with for globoidea. So this is a figure showing growth in the terms of productivity of mean top height. That's a dominant height of the height of dominant trees in a stand for regnans, which is in the blue, globoidea, which is in the red, and Fascicata, which is in the green, and over time as the stand goes. So you can see regnans gets off to a fast and furious start and has a really high mean top height, and then kind of cruises along at a pretty high growth rate over as the stand gets older and older. With the Fascicata has a slow start. If you ever plant a Fascicata, it kind of sits there for the first 7 to 10 years, then it just hits the accelerator and it's off. So you can see that height trajectory catching up to regnans on general nationwide scale by about 25, 30 years old. And you can see old globoidea kind of does its own thing and kind of slowly grows along with different ages there. But in terms of developing that natural durability characteristics, that's not a bad thing. Slow growth produces harder wood. But also for the globoidea, you're not quite aiming to kind of get that huge amount of volume. But it is growing at a good pace. So looking at the terms of stocking effects of looking at what this average size of the quadratic mean diameter of a stem is per hectare. Quadratic mean diameter is a way to kind of deal with the extremes, to look at it like an average value of the stand with increasing stocking. And you can see as you have more and more trees, as you expect, the diameter of the trees goes down, down, down. Now we can see with the regnans that any given stocking regime it has the higher quadratic mean diameter. But for the Fascicata and regnans, they're kind of more or less clumped just below that line. So I was like, oh, that's a bit of a aha moment. The quadratic mean diameter around 1,000 stems per hectare, well, I say about 800 stems per hectare for Fascicata is actually, using with projection lines, is actually lower than the globoidea. So, but interestingly, if you put this on a quadratic mean diameter versus DBH relationship, just to kind of see what's going on, you do get a closer relationship going on between the three different species, where they have, as the trees are getting bigger, more and more space. You got the regnans at the far end, like heavy, large, big trees. Well, you've got the globoidea and the Fascicata scattering along there, almost producing a one-to-one line. So even though you got Eucalypts from the ash group and you got from the stringybarks, there is some similarities in the in how they respond in the growth in terms of a nationwide scale. So there's this and other evidence from these measurements from the different stands. This shows that there is can use growth of some eucs like Fascicata to give an indication where other more sensitive site eucs like globoidea could grow or more likely not grow. So it's not saying that a euc is a euc is a euc, but it can be used, some species like Fascicata, as a general indicator of what other species could be grown in a particular area. And in terms of real data, this is looking at the terms of wood density taken at DBH from wood cores over for globoidea and regnans over different ages. As you can see very clearly here, the globoidea wood density is quite a bit higher than the regnans density. Fascicata density, if I remember the top of my head, is just a little bit higher than the regnans line there. So globoidea is far and away more dense than the globoidea, and most importantly, Paul, doesn't vary by region. So faster growing, slow growing sites, productivity sites, the wood density is pretty much about the same.
And I've got to just pause at this moment and say, Dean, what struck me is that if you relate the density figures and you'd alter that graph that showed the height. So in other words, while Reglands as a species is growing into a much bigger tree, if you're looking at carbon, it would be interesting to make some kind of a correlation between the two to actually demonstrate what's the total carbon they're growing.
Yeah, when I crunch those numbers, I think globoidea would be at the top.
At the top, okay? So it's slower growing, but higher density means more carbon. So if you were in the carbon game, you'd still be better off, even though the trees aren't as big. Does everyone get that?
And the correlation between actual timber weight per hectare would be basically the same, wouldn't it? So, so Reglands are fluffy and globoidea is a solid. The same.
Can you find a lot of air in the wood of Reglands? You're growing actual air in that tree, much less than the globoidea. Maybe it's a bit late even.
You're being paid per tonne.
Globoidea is NT
Yep.
Northland. So that's showing lower density. Is that almost the reverse for Reglands?
It's, well, to my surprise, there was some site variation, but I couldn't like pin it down to like a regional influence or not. There were sites where you could see it was growing like gangbusters, but the wood density numbers weren't that much off the average, to my surprise. I think we had some lower wood density numbers and some slower growing sites for some bizarre reason. So, but that was the biggest important data in terms of the wood density data is that not picking up productivity variability in terms of wood density was not occurring. So, so that's all well and good on a national scale, but also Paul will be itching to see how that site productivity varies by site for globoidea, and it's a lot of work with the dryland guys and Ewan's works going on there. This is data from 5 different sites from a 2003 Eucalypt stringy bark trial that was installed, and this is at various different sites at age 8. Through 5 sites throughout the North Island, so we can actually do a straight comparison without any confounding effects of age. As you can see, there is quite a bit of variability of mean stand height at that particular age. But what was interesting for me, I can see the Podigi site was the most productive as in terms of growing quite fast with a height around 20 metres, and then you have the Te Karaka site at the lowest end around 10 metres. But what was eye-opening for me in this one was that there was no one side that was horrible, like, you know, that the heights were like 5 metres or like really struggling along the way there. There was some confounding effects of site prep. I know the Te Karaka site suffered because it was on a dry site and there was no release spraying about a year or 2 after establishment, so it struggled through the weeds. So weed control is needed as well. If you say a site is good for high productivity or globoidea, unless you go back and actually give it a release after establishment, you're going to be losing all that good initial growth. So there is site variability in there, and there's definitely areas that are going to be more productive than others, and microsites definitely going to be come into that area importance as well. But it's not like for globoidea, like that one site is going to be fantastic and the rest of the sites are going to be crap.
What age is that data from?
It is, when did we click that? It's 2003, so that would have been 11 years old. Take that back.
So 11 years, so some trees are doing 2 metres a year on that Podigi site.
Yeah. I think that these sites are averaging, on average, about 8.9 cubic metres per hectare per year at this young age.
Is that Podigi site where you wrote off?
Yep.
We need to go there.
I hear that was very well looked after in terms of weeding. So where am I going next with this work? Well, as Paul jumped up in excitement earlier, carbon work. So we'll be taking all this information from the 3PG model in the terms of growing volume of a tree, put it into Peter Beach's carbon calculator to come up with those wood density models, to come up with some numbers for how much carbon is stored above ground and below ground, through carbon sea change. And that will, in the terms of MPI, give a good broad range of what globoidea could do in terms of carbon sequestration throughout the country at different regimes and different productivity. And this work can, this data could be, be used by the drylands folks in terms of not saying that the wood density data instantly equals good heartwood, but I see there's some good correlations in there. And what it can be doing, and if a good early marker of what globoidea can be doing in these older stands as these experimental series starts getting older. So in summary, process-based models is ideal for species with limited data sets, and also it gives a bonus if it's a dynamic model with static, can bring in new environmental data, climate change data, green site data, etc., etc. There are some strong correlations of growth and of responses to productivity, site productivity between globoidea and fastigata, which helps fills in the holes for globoidea. Globoidea is not as site sensitive as first fed, well, I was fairing, which is always a good thing. Globoidea has a higher wood density than the traditional ash group industrial Eucalypts, Eucalyptus regnans and fastigata, with no real regional differences. So next steps for me, finish 3PG parameterization for globoidea and regnans by the end of the month. And then create spatial productivity map that will identify highly suitable areas for those species. So using that information to provide a realistic productivity range for globodeia's potential in a general a general way, nationwide maps. By next year, the more heavy data is going to come out of those species trials, dryland species trials as I develop further. And finally, create a carbon sequestration model with globoidea and regnans by Chrissy. So this work just happens to work well and dovetails into the dryland forest work. Almost, you can almost say that's an independent check of what was going on there, making sure the Paul's not a snake oil salesman. But there's a lot of synergy, that can be done in this in this space, and I do enjoy having the opportunity to collaborate with the dryland forest group, with the University of Canterbury, and combining our resources to produce something high quality and useful for growers, as well as having good scientific rigor. With that, thank you.